I will just take a very few moments to introduce our speaker. Jenish is pursuing his PhD from Caltech in theoretical computer science, and before that he has done his BTech degree from BITS Pilani in computer science. And his main domain of interest and his main domain of research has always been mathematics and the mathematics behind computer science. He has also published many papers and always believes that if we have our fundamentals very strong, then we can actually master in anything. So some of the theories which he has actually written his papers are on complexity theory, spectral graph theory, logic and descriptive complexity, and circuit complexity. So he has written many research papers on these theories in computer science domain. And I would like him to share his experiences about his knowledge in computer science and what do he think that we as the students shall go forward with. So handing over to you, Jenish.
Hello. Yeah, can everyone hear me? So am I visible and audible? So should I remove my microphone or is the voice okay?
Yes, you are audible and also visible, Jenish. So
yeah, of course I'm visible. But is my like audio okay?
Yes, you are audible.
So let me just try out by removing it, okay? And then tell me if that is better. Okay, so now I'm speaking like this without the like earphones. Is this better? Or now I'm speaking is this better? Like which one is better?
Without earphone is much better.
I'll just remove my earphones, right? This is good for everyone, right?
Yes.
Okay. So okay, so just actually give me 1 second, okay? Okay, yeah. So everyone can hear me, right? Yeah. Okay. So hi everyone. So actually, I don't know what I'm supposed to speak about, really. So I just like made few things, and I will speak about that. And I think it will be best if you guys ask me any questions that you have. Like that will be, I think, the most helpful for you. Like I can say anything, I can speak for like 10 hours, but then I think it will be much more helpful if you can ask whatever you want to, like, I don't know, or I don't know if you have any questions. Yeah. So I have made some presentations. So it will just take, I think, 15 minutes or something. So I'll just talk about that a little bit first. So let me just start sharing that. Okay, yeah. So can you enable me to start screen sharing? The host is able. Yeah. Okay, yeah. So let me just share. Yeah, so I mean, in case something is not proper, you guys can just speak out and I will change. So, okay. So you can see my screen here, right?
Yes, it's visible.
Yeah, and I'll just say play. And I hope this is visible too.
Yes, it's visible.
Okay, good. Okay, nice. So like, I thought I didn't know what to speak about. So I thought I'll just say, and of course, like I thank all these people of Clique for inviting me to speak and whatever. Yeah. So so I'll just tell you some ideas about like some of the most powerful and fundamental ideas of the last 100 years in math and computer science, because this has been like uh, this has been somehow like the most beautiful thing in the history of all of sort of human thought itself. Okay. So I think it's mostly like a history, like it should, so hopefully it should be interesting. So let's just start. So I think this is sometime around the time of like 1900. Okay. So people had always been doing math in like different forms and different formats and everything. Okay. And people started asking this question that like sort of what is really mathematics, right? So Euclid did math using his geometry and everything, right? All of us learned like Euclid's axioms and everything in school and so on. And then we also do a lot of algebra. Then the way we do like geometry is different, right? Then there is also like, I mean, we do all these kind of different things in different ways. But like, what is mathematics really? Okay. So if so, like that was the most like basic question at like beginning of 1900, that like, what is mathematics? Okay. So like, does anyone have any, like, what comes to your mind if you think of mathematics? Like, what do you think is mathematics? So this is sort of a meta mathematical question. So but if you had to think through it, like, what would you say basically?
Numbers, number theory.
Okay, so you might say numbers. Okay, then I mean, that's what comes to people's mind, right? Because like the first thing that they learn as they're growing up is numbers, right? And they think that, okay, this is like the beginning of mathematics. Somehow mathematics is something where there are absolutely no numbers. Like mathematics begins where there are no numbers. So does anyone have any other thoughts or anything? So I think I can just like go on, because so you might think math is any specific thing, but like what mathematics actually is, it is just this thing basically. It's a method of writing like strings of symbols and modifying them. That's it. Okay. So basically you like write a lot of symbols and you play around with them to create new string of symbols, and that's it. So this is all that mathematics is at its like sort of very reductionist core. Okay. So now I want to actually give you people an example of like what this means actually, because I don't know whether anyone is familiar with how these axiomatic systems work and what does it mean, what does it mean to prove something and stuff like that. So I'll just give you a very small example. Okay, so we are going to start creating like a system of like something like a small mathematical system. Okay, so for example, so in our system we'll have many symbols. Okay, and I'm going to tell you a procedure of creating those symbols. Okay, so first of all, I'm going to tell you that this empty, that's the vertical line, and this dash, both of these are say valid symbols. Okay, so okay, that is fine. That's our first rule. And our second rule is just this very simple rule that say if S is a valid symbol, then if you put S in brackets, that's also a valid symbol. Yeah, is this clear to everyone? Like, yeah. So for example, yeah.
Uh, uh, I couldn't understand about the second one. Like why the S within the comma, sorry, within the bracket is a valid symbol.
Yeah, it's just a rule I'm making. So my 1 and 2 are just the rules I'm making. I can just make any rules, right? So I'm just making these rules that if I have a symbol, so these two are just rules. Like you can change the rules and you'll get some different system. So these are just like our assumptions. Yeah. Okay. So basically this is fine. Okay. So let's see what kind of symbols will this like system have. So first of all, you will have dash, because dash is a valid symbol. So this is a valid symbol. Now I can put dash in brackets, right? Because now I'm using rule number 2 above. So bracket, open bracket, dash, close bracket is also a valid symbol. It's like a valid string of symbols basically, right? Because my dash was a valid symbol from 1, and then from 2, this is a valid symbol. But now if this is a valid symbol, even this is a valid symbol, right? Because what I've done is I've just applied 2 again to like that. So if I apply 2 to the second line there, I'll get the third line, right? So this is also a valid string of symbols. And I can keep doing this. I can add one more bracket, and this is also a valid string of symbols. And so on. I can do this like n times, right? So I'll have like n brackets on each side. And all of these are like valid strings of symbols. Yeah. Okay. Similarly, I can do the same thing with dash, right? I can have a dash, and then I can have like brackets around it, because I can start with a dash, and dash is a valid symbol. And once I have started a valid symbol, I can put brackets around it. So that's also a valid symbol. And then that is also a valid symbol, and so on. I could put 3 brackets, and I could put so many brackets. Okay. However, but then how is dash different from the vertical line? So the thing about the vertical line is that it's the empty symbol. Okay. And because it's the empty symbol, I can just remove the line. So basically I can just like, the first thing is nothing. The second thing, I just written the brackets without the line. The third thing, I'm just writing the brackets without the line. Basically, line is like something which you can just remove if you want, because it's an empty symbol. So it's just like nothing. Okay. So, but don't need to bother about that. But like just so it's clear in your intuition what's happening. Okay. So these are my two rules. So now apart from these two rules, now I'm going to add like a third rule. Okay. And the third rule is that if S is a valid symbol, then that thing is also a valid symbol. So you first like sort of have the right bracket, then you take S, then you take the left bracket. So that is also a valid symbol. Yeah. So for example, this is a valid symbol. Okay. Why is this a valid symbol? Because I can start with a dash, which was a valid symbol. Then I keep applying 3 repeatedly n times, and I get that, which is the next valid symbol. Yeah. Everything is clear. Like basically, I hope everything is clear, right, so far?
Yes.
Or, yeah.
I think it's. If anybody have any questions, then you can interact. Okay.
Yeah, I mean, this is something very simple, right? I'm just telling you, I'm just describing a method of creating different strings of symbols. Like that's it. And I have just like starting symbol, which is a dash or an empty or nothing basically. And then you can just keep like, yeah, someone raised hand.
Yes,
Swat.
Swasti. Swasti,
Yeah.
yes.
Swasti, yes. So I had a
Yeah.
question. So if you look at 2 and 3, so this
Yeah.
S and S in bracket or S in inverted bracket, so these denote different things or are they the same thing?
They are different things, right? Basically, it's like, so imagine you have a set of, so imagine you have this set S. So imagine you have a big universal set U, okay? And U will be all strings that you can make using open bracket, close bracket, and dash, for example. Okay, so there'll be infinite strings there, right? Any string that you can make there will be there. So you'll have infinite strings. Now, what I'm telling you here is essentially what are the strings that are in our mathematical system. Okay, so S could be any valid string of symbols. Okay, so for example, you can start with any S, and then if you put brackets around that string of symbols, then that's a new valid symbol. Did I answer what you were asking?
Yes, thank you.
Yeah. Okay. So basically, it's just think in your mind. You start with something, some very simple thing, and you keep applying these rules, and you create different strings. Okay. And now we can also create the following string. We can also create a string like this, where you have mixture of brackets, right? Because say I start with a dash, then I use rule 2, so I'll get 2 brackets. Then I use rule 2 again, then I'll get 2 brackets. Then after using rule 2 twice, I'll use rule 3, so I'll get those kind of brackets. And then I'll use rule 2 again 3 times, so I'll get this kind of string. But this is also a valid string in my system, right? Because like all I'm doing is I started with 1, then I applied rule number 2 3 times, then I applied rule number 3, then I applied again rule number 2 3 times. So any string like this that you can imagine of any length is a valid string. Yeah? Is this much like clear to everyone? Like it's very simple, right? There's not we are sort of not doing anything so far. Yeah. Okay. So okay, I'll just go on if there are no more questions. So basically, you have something like this. Okay. And now what I'm going to do is something like the following. So now, so these are our 3 rules so far, right? Blah blah blah. S blah. Now I'm going to add more rules. Okay. And the rules are as follows. The 4th rule is the following. If I have 2 dashes, that's just same as 1 dash. Okay. Then the 5th rule is the following, that if I have like the left bracket and dash, then that is same as just having the left bracket. Okay. Which means I can just remove the vertical dash, as I just said, right? You can just remove the dash whenever it's there, right? The rule number 6 is also the same. If you have a dash and then if you have a right bracket, then you can remove the dash. So these are just like these things are fine. You can just keep removing dashes as much as you want. Okay. Now rule number 7 and 8 are going to be special for us. Okay. So what is rule number 7? If I have an open bracket and a closed bracket beside each other, then that will turn into a dash, into an empty symbol. Okay. And then 8th rule is also very nice. It says that if I have like an open bracket, I mean, if I have like a right bracket and then a left bracket, that will also turn into a dash. Okay. So these are just what I told you. First I told you that okay, I just have basic base symbols, which is just a dash, which is a horizontal line, and a vertical line. Okay, which is I just call it a line, empty line. So you have a dash and a line as valid symbols. Then you can use rule 2s and rule 3 to like put brackets or inverted brackets or whatever around the string, and you'll get like different strings of symbols. Yeah. And then 4, 5, 6 are saying nothing. They're just saying that the line, you can remove them wherever it is. It doesn't matter. And rule number 7 and 8 are nice. They are saying that somehow the open bracket and the closed bracket cancel each other. Okay. So that's what 7 is saying, and that's what also 8 is saying, that if first you sort of have the right bracket and then the left bracket, then they basically like close each other. Yeah. So this is something that we have here, right? So now these are our rules, and I put them on the top. So I hope everyone can see all the rules. Yeah. And now, so this is our mathematical system. Okay. And now we are going to prove a theorem. Okay. So what is our theorem going to be? So my theorem is the following: that the string on that left hand side, you see that big string. Okay. It's a valid string of symbols, right? You can check that, because I can start with a dash and I have equal number of right brackets. I have like 1, 2, 3, 4 right brackets and 4 left brackets, which is fine. I'm looking on the right. Then I have like 2 left brackets, then 3 left brackets. Then I have like 2 right brackets and then 1 left bracket. Basically, I have this string of symbols like this on the right of dash and on the left of dash. So this is so the string on the left hand side here is a valid string in the language. I'm saying that string is equal to just the dash, just the original symbol string. Okay. So I'm just saying that these are 2 strings of symbols in my mathematical system, and both of them are the same. Okay. And now I'm going to show you what a proof will look like. Okay. What is a proof of this statement? Okay. So the proof is the following: you start with the original string. Okay. And now you see those 2 brackets in blue that I have marked there in our string, right? There are those 2 brackets in blue, like they start with the 3rd bracket from the left, right? And because they are like that, right, you can apply 7 there and you can put a line instead of those 2, right? So in that string, what I'll do is I have removed that string, those 2 things, and I put a line there. Everything else is just the same. Right? My rule number 7 says that if I see an open bracket and a closed bracket, then I can replace them with a line. So that's what I did. Okay. Now I'm going to use my rule number 6. Okay. What does my rule number 6 say? If I have a line and a closed bracket, I can change that to a closed bracket. Right. So I'm going to apply rule number 6 on those 2 things, and then I'll reach that. Okay. I'll reach the following string. Yeah. Is everything clear? I'm doing something very simple. I wrote a bunch of rules. Now I have a string. I can apply the rules in any manner I want. Like I can start with that thing. I could start with from the right hand side, those right brackets or something. I could start from anywhere. Okay. But wherever I can apply a rule, I'll apply. Okay. So then I reach the following string. Now, if you see those 2 close and open brackets in blue, right, I can apply my rule number 8 there and replace them with a vertical line, right? Because my rule number 8 says that I can remove those 2 brackets and put a vertical line. Okay. So I took those 2 brackets, I put a vertical line, and then vertical line I can always remove, right, by using 4, 5, and 6. So I just removed it. Similarly, I'll apply 8 again on those 2 brackets, and I'll reach that. Then I'll apply 8 again on those 2 things, basically, and I'll reach that thing which you see there, right? And on the remaining 2 brackets, I'll apply 8 again, and they'll be removed, and I'll reach that string there, right? So if you see, everything on the left of dash has been removed, right? Just by applying the rules that I wrote there, right? Yeah. Similarly, what I can do is I can like now start from like now I can just look at, I mean, I can pick anything in this remaining string. If I can reduce anything, if I can simplify my string, I'll keep simplifying my string. Okay? So if you now look at all those 2 brackets in blue, where one is like a right bracket and one is left bracket. Okay? And if you look at those 2 brackets, and then I'm going to remove them. And once I remove them, I get the resulting string in the next line. Now in that last string there, I'm going to take that open and close bracket, which is in blue. And by using rule number 7, right, I'm going to reduce it. I'm going to remove it. Then I again, now if you just see, I just have 3 sort of closed brackets, 3 open brackets. So basically I'll just be able to apply rule number 8 3 times, right? I apply it once and those 2 get removed. Then I apply it again and then those 2 get removed. Finally, I'm left with those 2 and I apply rule number 8 and I'm left with a dash, right? So this basically, this proves that whatever you have on the left is exactly same as what you have on the right. So this is your proof, right? So what did I do in the proof? So I have strings of symbols. I took like some symbols on the left. I took some valid symbols on the right, and I showed that they are equal, right? Yeah. Anyone has questions in this proof, like what we did here? So everything is clear, right? So then I can just continue. So basically, this is what mathematics is basically. Okay, that you have some rules, then you have some theorems, and then you have proof. What is proof? A proof is just a repeated application of rules to go from the left hand side in the theorem to the right hand side. Okay, and if you realize what we have done here, what we have shown here is actually 4 minus 3 plus 1 minus 2 equal to 0. What we have proven in this theorem is that 4 minus 3 plus 1 minus 2 is equal to 0. Okay?
How?
So, because you see, it's like we had 4 open brackets, and the moment you have an open and a close, so it's like rule number 2 is like addition of 1. Rule number 3 is like subtraction of 1. And then my rule number 7 and 8 tell me that whenever I have 1 minus 1, it should become 0. Whenever I have minus 1 plus 1, it should become 0.
Okay.
So this is yeah.
Hello.
Yeah.
So you mean that the right bracket and the left bracket, these are 1 and minus 1, like it is represented by 1, right?
Yes. Yeah, so the right and left bracket are acting, they are behaving as if they are plus and minus 1. Yeah? You're right. So it's like if you put 2 right brackets, it acts as plus 1. And if you put 2 like left brackets, basically inverted brackets, then it acts like minus 1. Yeah. Exactly. So that is how these things are behaving. But you see, there are no numbers here. Yeah, inverted. Yeah. So there are no numbers at all. But you can do everything that you would otherwise do with numbers, right? Now, because you have this, you can do like anything you want here, right? Now let's see one more theorem just to understand what is happening. Okay? This is a much simpler theorem, which says that if I have brackets like this, then that is just equal to the vertical line. Why should this be true? Because this is very simple now. I can just quickly write the proof. Like in the first line of the proof, I'll just apply rule 5, and I'll come to those open and close brackets. And then when I open and close brackets by using rule 7, they'll become a vertical line. Okay. And if you see, my first line had 5 brackets on both sides of the line. And in that thing which is marked as 7, where I used rule 7, I have 4 brackets, right? So now I can keep applying 5 and 7 repeatedly, and I'll reach the vertical line. Yeah. So this just tells you basically that, so what is this? What is happening here? This tells you that this guy is behaving like a 0. Okay? And this was like multiplying by 0. It was as if you took some number 5 and you multiplied it by 0. Okay. So your vertical line is somehow behaving like a 0. Okay. In this system. But you see, this is how this is what mathematics is about. Okay. So this is what they actually figured out at the beginning of 1900. Okay. That mathematics ultimately is this. Okay. That you have some rules. So you have 5 rules or 10 rules. But after I give you these 10 rules, you should be able to describe everything in mathematics, whether it is algebra or geometry or number theory. You see, this describes all of number theory, right? Any theorem in number theory, I can write it using this mathematical system that I created. So basically, this represents all of number theory. So you would want to represent geometry using the same things, not some different. You might add more rules, but you have just one system of rules. Okay. So the current system of rules that all of us have been using were formulated sometime in the 1920s or something, and that system is actually okay. Actually, I have one more example. So let me just say that example so you can understand how strange these systems are. Okay. Now I removed the dash as a symbol. I just have the vertical line as a symbol. And then I have my rule 2 and rule 3 as they were, that if you have a symbol S, then you can have open and close brackets. But my 4, 5, 6, so now look at these rules. These are very different rules. Okay. My 4th rule says that if I have a vertical line, I can just remove it. It's equal to nothing. But now my rule 5 says that instead of one open and close bracket being one line, I'm taking 2 open and close brackets and they will become a vertical line. Similarly, my rule 6 says that you can take 2 brackets like this and they'll become a vertical line. My rule 7 says that if you have a close bracket, open bracket, that is equal to a close bracket, open bracket, close bracket. And similarly, I have written say more rules. I have rule number 8, rule number 9, rule number 10. Yeah. So I have written Yeah, so this is some other system, right? So basically, like you have like this is some new system that I created. Okay, so let's see what we get here. Okay, so here we can start. So these are our rules now, and this is the same string that we started with in the previous case. Okay, this is 4 minus 3 plus 1 minus 2. Okay, let's see what we end up with here. Okay, so now we can start with the original thing, and we can apply rule number 9, right? That if we see that like close bracket, open bracket, open bracket, sorry, open bracket, close bracket, then I can change it basically to whatever you have on the right. So I am going to start by applying that rule, and I'll get I'll get the string which is there, and I'll again apply rule number 9, and I'll get that string. And once I get that string, I'll apply rule number 6, where I can convert that whole thing in blue to a vertical line. Okay, so that whole thing became a vertical line. And by rule number 4, I can just remove the vertical line wherever it is. So it'll become that resulting string. Now in that string, I'm going to apply rule number 8. So I'll get that. Then I'll apply rule number 6. I'll get that. I'll get a vertical line which I can remove. Now in that resulting string, I can just apply rule number 9 3 times. So I'll get that string. Now I apply rule number 6. So I get that. I apply 8. I get that. And in this resulting string, I can apply rule number 5, which says that those 4 brackets will become a vertical line. So they'll be removed, and I'm left with that. Right. So this shows that 4 minus 3 plus 1 minus 2 is equal to minus 2. Okay. The previous thing showed that 4 minus 3 plus 1 minus 2 was equal to 0. This system shows me that 4 minus 3 plus 1 minus 2 is minus 2. So this is just a behavior of symbols. Okay. There is no one is right and one is wrong. Both of these are right. Okay. If you change your rules, your theorems change. If you change any rule even slightly, all your theorems will completely change. Okay? So this is how mathematics works, and this is what mathematics is. Okay, that you have symbols, you have few rules to modify those symbols, and you keep generating theorems out of those things. Okay? Whatever you have in the theorem is the truth. Okay, it doesn't matter that like whether it makes sense to you or not. Okay, yeah. So now you see how sensitive these things are to your rules, right? So what rules should we select so that we get like a kind of a system which we can somehow use somewhere? Okay, and that present mathematics. So this is the only example I had. Basically, now I'll just say a few things. So that present mathematics is embedded in these like Zermelo-Frankel axioms. Okay, so all of us, whatever we use, is actually these Zermelo-Frankel axioms. Okay, and actually like basically like okay, so this is the axioms that we use. And there is one more axiom that we use, and that is called the axiom of choice, okay, which is very, very fundamental. And it's sort of the most remarkable axiom. It basically says something to the effect of that if you have a collection, if you have a set, okay, you can always pick an element from a set. That is the axiom. That is not at all like trivial because, yeah, so these axioms are very, very subtle. So unless you come like, if you are doing something and you realize, oh, I need some axiom, and you arrive upon the axiom of choice by yourself, if that happens to you, then certainly the axiom of choice makes sense to you. Otherwise, if I just tell you the axiom, it won't make so much sense, like intuitively what it is. So, but okay, basically you have some axiom of choice and you have these axioms. So these are total of like 5 axioms. Okay. So Zermelo-Frankel are actually like 4 axioms. Okay. And then axiom of choice is like one more axiom. Okay. So basically there are these 5 axioms. And using all of mathematics that we use today uses just these 5 axioms. Okay? There are just 5 rules. There are strings of symbols and there are 5 rules. This is all we use. Okay? And now we can try and prove something like the following. Okay? Given those axioms and that axiom of choice, okay, what is 1 plus 1? Like give me the proof of 1 plus 1 equal to 2. Okay? So if I ask any of you, what's the proof of 1 plus 1 equal to 2? Like what will you say basically?
I mean, it has been so trivial thing that I have never thought that anybody will ask me that 1 plus 1 is equal to 2.
Yeah, because you don't know what 1 is, right? So you just think 1 is some number, but there is no 1. It's just a symbol. So you have one symbol on the left, which is 1. Then you have another symbol, which is a plus sign. Then you have a third symbol, which is 1. That is what you have on the left-hand side. Then you have an equal to sign. And on the right, you have a completely different symbol, right? So there is some system which has these symbols. Somehow someone has put these symbols together. But using the rules of the system, that Zermelo-Frankel and axiom of choice system, you should be able to prove this. Okay, and the proof of this is over actually 400 pages. Okay, So you are going to use the Zermelo-Fraenkel system axioms, and including the axiom of choice, and you can prove that 1 plus 1 is equal to 2. And this was basically this was done in like Principia Mathematica by like Russell and Russell and Whitehead. Okay, so they had this Principia Mathematica wherein they proved this. So it took them over 400 pages. Okay. The next theorem I can ask you is like, what is -1 into -1? So now this is another theorem, right? Your minus, then your like 1, then you multiply, then your minus, then your 1. Okay, then I've written equal to, and then I've written plus and 1. Okay. So what is the proof of this thing? Like, how will you prove this thing? Do you have any guess on how long the proof of this thing would be? You can guess anything.
About 400 pages.
Sorry, what did you say?
400 pages or more than that?
Yeah.
About 400 pages or more than that.
Yeah, maybe. Who knows? Yeah, it could be more than 400, right? Surprisingly, the proof of this is only 2 lines. Okay? And actually, you all should know how to prove this. Okay? So the first theorem, if I give you the first theorem that 1 plus 1 is equal to 2, okay, that's not a theorem. So imagine you don't have to prove that, and you took it, and then you had to prove the next theorem. It's like just like it's like a grade 8 exercise. Okay, if you are in grade 8, in 8 standard or whatever, then you can show this in just like 2 lines basically. So I think you should all try and prove this, because you should all be able to prove this. So now this is what was happening in 1920s. Okay, so people realized, okay, we have axioms, and then we will have theorems. Okay, very good. So now, can we prove everything that is provable? Okay, like this was like one of the big like sort of like projects in all of mathematics, that how will you formally prove stuff, right? What I showed you was a formal proof. Okay, first of all, people didn't even know what a proof is. Okay, so they defined a proof as a sequence of application of rules. Okay, and that is a proof. Okay? And then there was this shocking theorem which came in like 1931, and it was by Kurt Gödel. This is probably the like most fundamental theorems of the last 100 years. And probably in all of mathematics, it's one of the most fundamental theorems ever. Okay? And it was by Kurt Gödel. And this theorem basically says the following, okay? That it's called the Incompleteness Theorem. It says that any axiomatic system, like the one I showed you, cannot be both consistent and complete. Okay? So what does it mean to be consistent? It means that any theorem you can any theorem that you can prove is actually true. Okay, that is the meaning of being consistent. And complete means that any true theorem you can actually find a proof. Okay, so basically, if there is a theorem which is true, then there is some sequence of application of rules by which you can prove that theorem. Okay, it shouldn't be that you keep applying rules infinite times, but you still can't prove the theorem. Okay, imagine that example that I gave you. We had some string on the left. If we kept applying rules again and again and again and again and again, but if we never reached the right hand side, that would mean that, okay, that's a true theorem which doesn't have any proof. Okay? So that shouldn't happen. Basically, it should be complete. And you would also want the left hand side, that it should be consistent, that everything. So consistency just means the following: you shouldn't be able to prove that A equal to B and also A not equal to B. Okay, if you can prove both these things, then it is not consistent, right? You should be able to prove only one of those things. Okay? So this is like, and what he showed is that you can never have this in mathematics. Okay, so any axiomatic system that you start with, okay, if you have a finite number of numbers, so there is some technical caveat, okay, but given that that is true, which always has to be true, otherwise the system will never be powerful enough, then it won't be both consistent and complete. This means, what does this mean ultimately? That there are theorems which are true, but you can never prove them using any mathematics. These are mathematical theorems, but they can never ever have a proof. Okay? Or if you try to change your axioms to so that those things have a proof, you will end up having a theorem which is both true and false. So this was shown in this was like the most fundamental, like, I don't know, theorem like in all of history of math. Okay? And if we look, so this was about like, what if I give you a theorem, is there a proof? Okay? If I ask you, is there a proof? Then this is what it was about. Okay. And if this question is a domain, this question is within the domain of mathematics, right? If I give you a theorem, is there a proof? What do I mean by is there a proof? Is there an application of rules to your symbol so that you can reach the right hand side from the left hand side? Okay. So that is a proof. And now the second question that you can ask, which happened immediately after Gödel published his thing in 1931, was how to find a proof. Okay. Imagine I told you that there is a proof. How can you find a proof? And this is actually the birth of computer science. Okay. And this, everything that anyone ever does in computer science, any algorithm, any code that you ever write, is actually writing a proof for something. Okay. It's actually a proof in some axiomatic system. Okay. So this thing was about like how to find a proof. Okay. And then in like 1936 was the next paper by Alan Turing. Okay. And which was similar papers were already published around the 1931 to 1936 by like Church, Klein, and Emil Post and everyone. Okay. And what this is Turing, and what they essentially showed, that there are theorems for which there is no method which will actually find a proof. Okay. Which means there will be a true theorem for which there cannot be any algorithm ever, okay, which can prove the theorem. Okay. Imagine I give you some theorem and I asked you to write a code to prove that theorem. Okay. This showed that there are like theorems for which you can never have. These are mathematical theorems, okay, well-defined mathematical theorems for which you can never ever have a proof. Basically, he showed it for this halting problem. That like imagine you have to write a program. Okay, your program is P, and you can write it in whatever, Python, Java, whatever. And your program has to do the following. Your program will take two inputs. It will take a text file, which will be another program. Okay, it will take that text file as an input, and it will take some string. Okay, which that program is A, the text file is A, and the string is X. Okay, and both of these are given as an input to your program, and your program will just have to say yes or no. Basically, if that program A halts on X, you'll have to say yes. If A does not halt on X, you'll have to say no. What Turing showed is that you can never write a program like this. So this is not our limitation. This is impossible. It's mathematically impossible to write a code like this. Okay? Basically, from now till forever, such an algorithm will never be written. This is actually profound and phenomenal. Okay? Basically. And this is actually all of computer science, okay, essentially, at its heart. And then I can ask a very broad question. Okay, all of you should, this is a very simple question, because proving this question is same as giving the proof of what Turing gave. I'm not going to give you the proof, but this is a very simple question, okay? So let n be the set of all natural numbers. Okay? So n is just like 1, 2, 3, 4 infinite numbers. Okay? Now let f be the set of all fractions. So f is the set of all like 2 by 3, 5 by 7, 55 by 87, whatever, all fractions that are there. And let r be the set of all real numbers. So r will have like 4.896245. Then it will have pi, it will have e, it will have everything, e raised to pi, everything. R will have everything. Yeah. Now these are three sets. All three sets are infinite. Okay. But if I had to ask you, are there more fractions than natural numbers? Is it true or false? I'm asking, are there more fractions than natural numbers? Will you say yes or no? You should guess actually. If you had to bet, like if you had like, I don't know, whatever, 100 rupees.
It should be yes. I think it should be yes.
Okay, you think it should be yes intuitively, right? That there are like more like fractions than natural.
Yes, if you consider a particular range, say for example, then in that particular range, number of fractions will be more. And like that, we can prove that if the range is infinite, then also the number of fractions will be more. That's what I.
No, but in a but how can you prove even in a but okay, I'm not giving you a particular range, right? Because then I can just take range between say 1.5 and 1.6, and there are no natural numbers. But the question is all natural numbers, right? Like if these sets, so if one set has size 2 and another has size 3, then there is no point in comparing them. Then you know that okay, another set is bigger. Here all sets have infinite size. Okay? Then is f set of f size of f more than size of n? Okay, you can guess it's yes. And then what about real numbers? Is the size of r more than size of f? Would you say yes or no?
Yes.
Yes. Okay. Yeah.
Yes.
Yeah. So now I'll just tell you what is. I mean, this is very simple to prove. The total number of natural numbers is exactly equal to the total number of fractions, and both of them are strictly less than the total number of real numbers. This is beautiful, actually. Okay, this is called the diagonal argument. It's the same argument. To prove this, it just takes like one page to prove this thing, and it's the same argument used by Turing. It's the same argument used by Gödel. And before Gödel, this thing, what I've written there, was proved by Georg Cantor, the set theory, the guy who proved, like from whom we got set theory in 1800s. He proved this thing, and it's exactly the same proof. Cantor, Gödel, Turing, all three proofs have the same thing. And basically, now because we had, what's the question? Yeah.
I have like, how can natural number, set of natural number and set of fraction number f can be exactly same?
Yes.
Because fractions will be much more, right, than natural numbers.
But what? Yeah. So it's like it's like, you see, when two sets both are infinite, what does it mean to be much more, right? Like, what does it mean to be much more, right? Like, both are infinite. So you see, it's like this. It's like, because so what you'll have to define are multiple types of infinities. What we have is only, there is not one type of infinity. There are multiple types. There are infinite types of infinities. Okay, and the size of natural numbers is equal to the first infinity. The size of fractions you can show is also equal to the first infinity, which means both the size of natural numbers and fractions is the same. And the size of real numbers is equal to the second infinity, which is more than the first infinity, basically.
Okay.
So it's like, it's completely counterintuitive, but if there is a proof, like the proof I showed you, right? Like there are rules, then there's a theorem, and then there's a proof. There is exactly a proof like that by which you can show that the number of fractions is same as the number of natural numbers. Okay.
Okay, now I have like one more question. So let's say if you think in terms of infinity, then suppose, since you don't know when the infinity will go to, so then you can also say, right, that okay, that the set of real number is also like goes to infinity. Then ideally we can also say that n, f, and r kind of like same, like the length is same. Similarly, like the way you showed n equal to f.
Yes. No, exactly. But so that proof will not work for real numbers. That proof will work only for fractions. It won't work for real numbers. And the main reason is the following. Like when I write a fraction, right? It's like when I write a real number, after the decimal, I can have infinite digits, which never repeat again. Okay? Like for example, if you write root 2, okay? If you write root 2, then you'll have 1.414 blah, 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 but you'll never have a repetition. Yes. In any fraction, you'll start having repetitions after some point. Okay, so essentially any fraction is just two numbers, right? Any fraction is just a collection of two integers, right? And you can always show that you can map one to the other. Okay? For example, if I ask you another, let's take these two sets, okay? One is the set of all natural numbers. That is one set. The second set is the set of all even numbers. Okay? Is the size, so that let the first be n, the second be e. Okay? Is the size of these two same or different? You should be
different.
You should be able. They are the same.
Yeah, because
you should be able to prove actually that they are the same somehow. Yeah. Actually, it's a beautiful thing by Georg Cantor, and it's just it's a very simple thing. I can even describe the proof. Yeah. So the key thing
but
is
like how, because
the main thing is understanding when will you say
natural numbers have like 1, 2, 3, right?
Sorry, what? So
let's say if you take a subset of a natural number, so then it will let's say 1 to 5. Okay, so 1, 2, 3, 4, 5. And now if you take that kind of subset in even number, it will only contain 2 and 4. Then accordingly, if we can, according to that, if we like maximize our window size, then we can prove that E is lesser than N.
No, but only for any finite window size, E is less than N. But when both are infinite, E is equal to N. Okay, now you can prove it very simply. So now, so imagine I give you two infinite sets. Okay, how will you show that both of them are the same size? Okay, So the first thing that you will do, okay, so I can just tell you the proof of why E is equal to N. Okay, the size of E is equal to the size of N. Okay? So when will I say that two sets, okay, have the same basically size? I'll say that when I can prove two things. One, that size of E is less than size of N is less than size of E, and size of N is greater than size of E. If I can prove less than equal to size of E and greater than equal to size of E, if I can prove both of that, that would mean that size of N is equal to size of E, right? Yeah. So yeah. So if I give you two sets, okay, how? Yeah. What are you saying? Yeah.
So it depends upon the window size exactly, right? Like your window size should be infinite.
No. But you don't have any window here, right? You have all natural numbers and all even numbers.
The whole.
Yeah. Forget window. Like window, like everything is trivial if you have a window. Yeah. So you don't have any window at all. Okay? So you just have infinite natural numbers and infinite even numbers. Okay? Then how will you show that they have the same size? So basically, imagine I give you any two sets, say for example S and T, okay, and both of them are infinite size. Okay. If I can map every element of set S, okay, to some distinct element of T, okay, yeah, or basically if I can map every element of S, or basically if I can map every element of S to some distinct element of T, I can show that size of S is less than or equal to size of T, right? Because for every element of S, I have some element of T to which it goes to, right? So that tells me that size of set will be less than size of T. Size of S will be less than size of T, right? This is fine, right? If I give you two sets, okay? Imagine you had, in this set I had numbered 1, 2, 3, 4. In this set I had like apple, orange, banana pair, and say lemon, for example. And then I might map 1 to banana, 2 to apple, 3 to say lemon, 4 to pear, okay? I mapped everything here to some distinct number on the right hand side, which means my set, the size of thing on the left is less than size of thing on the right, right? It's less than or equal to. Yeah.
Yes.
Yeah?
Yes.
So now let's take the first set as the set of natural numbers. Okay.
Okay.
Now, and so that's my set on the left, and on the right, my set is the set of all even numbers. Okay.
Okay. Fine.
Now I'm going to say that I can always map every natural number to some unique even number. Okay.
Yes, you can.
You always can, right? So I can always map 1 to 2. I can map 2 to 4, 3 to 6. Any natural number that you tell me, say you tell the natural number 12, then that's mapped to 24. If you tell, so my size on the set is at most the size on the right. So size of set on the left is less than or equal to size of set on the right. Similarly, you can do the other way around. Every even number you can map to a natural number by dividing by 2. Like you take an even number, say 24, that maps to say 12. If you take, say, for example, 26, then that maps to 13 and so on. Which means these sets have the same size. So mod S, like it's like mod N is less than or equal to mod E, and mod N is more than or equal to mod E. So mod N is equal to mod E. Now, if you see, this proof holds only if both are infinite, right? It won't hold if you have any finite thing, right?
Yes, now I understood.
Yeah,
okay.
So that's, yeah. So it's the same way you can create a map, even between natural numbers and fractions. So if I give you natural numbers and then if I give you fractions, you can create a map and show that for every natural number, there'll be a unique fraction, and more, which is very easy, right? I can always map my number 5 to 5 by 1. I can map 7 to 7 by 1, so on. That is very easy. But I can also map every natural number, every fraction to a natural number, unique natural number. So you have to create that map, okay? And then once you create that, you've shown that they have equal size. It's called dovetailing. You can do that and you can show it. And the beautiful thing is, to show that reals are equal to natural numbers, you can show that there cannot exist a map. Okay, you can show that if there exists a map, then you can show a contradiction. Okay? So you can show that there cannot exist a map. So that's how you can prove that thing that I had shown. So this is how all these proofs go. Basically, this is somehow the basis of everything in the universe. Like not universe, but everything that human beings know of. What I'm telling you here, basically, it's like how axioms are there and how you play around with them, and then what kind of theorems you get, basically.
Okay, got it. Thank you.
Yeah. And now I can like basically go to like the third thing, which question, and the question is how fast can you find a proof? Now I have just one more slide left, so I'll just say about that. Okay? Like how fast now, imagine I told you that there is a proof. Okay, I told you there is a theorem, and because there is a proof, because we know that there are theorems for which there is no proof. But imagine I told you that there is a theorem for which there is a proof. Okay, but how fast can you find a proof? And this takes us to a beautiful example, okay, which I'll tell you, which is so shocking, okay, because this will give you the birth of the third field, which is like as fundamental. All these three are the same things: math, CS, or next thing which I'm going to come to. Okay. So now imagine it's a very simple setup, and everyone who writes code will know this thing. Okay, imagine you have 10,000 cities. Okay, and between different pairs of cities, you know the length of path. Okay, that between A and B, the length of the path is 5. Between B and K, the length of the path is 24. Between C and U, the length of the path is whatever. So there are 10,000 cities, and between different pairs of cities, you know the lengths of the paths. And now you would have come across this thing in all your algorithms courses and everything, right? This is very simple, right? If I ask you a very simple problem, what is the shortest path between some city A and B? Okay. Then how will you solve this problem? This is very simple, right? Like, I mean, if I ask you what's the shortest path algorithm, right? You would have come across this thing somewhere or the other, right? Like you use the Dijkstra's algorithm, or you can use Floyd-Warshall, or you can use anything. You can even modify BFS enough to like do this, whatever, right? And this basically can be solved in less than 2 seconds. Okay, this problem. Now I'm going to modify the problem slightly. Okay? Instead of the shortest path between some city A and B, okay? Note that the shortest path between there might be no path between A and B, so you might have to go through other cities, right? The shortest paths also. Now, if I ask you the longest path between some city A and B, I don't want the shortest path, I want the longest path that you can find. So how much time do you guess will this problem take? Like that thing can be solved in less than 2 seconds. So this thing can be solved in like, how much time do you think it will take? You should guess, like you should imagine if you had to bet $100, like you had to bet like whatever, 100 rupees on whether like this is true or false. Like, I mean, how much time will this take? What will you bet on, basically?
This time will be varied. I mean, there cannot be only one longest path, but there can be one shortest path. I mean,
no, there may not also be one shortest path, right? There could be infinite shortest paths, but you have to find only one. Similarly, there could be many longest paths, but you have to find only one. You don't have to find all longest paths. You have to find only one longest path.
It should be greater than for the problem one, I guess, because we need to map like most number of cities that I have to go through also.
Yeah. That is true.
So it should be greater than the problem one, but
yeah. But like, okay, it is greater than problem one, but what, I mean, if you had to put a bound, okay, like the bound is the following, okay, that any algorithm from now till forever, okay, it's not about computers or algorithms or technology, or there's a progress in technology, so now things will become fast. That is absolute nonsense, okay? Any algorithm for this problem will take more time than the lifetime of the known universe. The known universe is about like, I mean, that's also stupid that it's like 15 billion years or whatever, which is again very stupid. It's just a theory. It's not the truth. So this is another thing which I wanted to say about, because which is very crucial and fundamental. Okay. And that is like in math, you have a proof. In science, there is no proof. Okay. Science is inductive. Math is deductive. Okay. So there is no proof for anything in science. So everything in science is essentially an assumption. So there is evidence in science. Okay. If I see something falling 10 times, if I throw like a coin and it falls 10 times, then I can say it's an evidence that things fall down. But it's not a proof that things will always fall down. Okay. Then for example, there is some theory that there was a big bang and then the whole universe was created and something like that. But personally, I find it completely rubbish. Okay. It's also a theory. Okay. Which based on some experiments, you make that theory. But people start believing these things as if it's the truth. There is a proof for that thing. There is no proof. There can never be a proof for anything scientific. So everything scientific is always an assumption. There is no proof. Okay? There is an evidence, but it doesn't mean everything will always happen that way. Okay? So math is very different. Okay? Here, what we are going to say is the following: that any algorithm that you can write for this problem ever will take more than like say 1,000 billion years. Imagine you just have 10,000 cities. Okay? And if you write this algorithm, it will take so much time. So if you understand what is happening, it's not that, okay, we are not intelligent enough and we are not writing fast algorithms, or that we don't have fast enough computers. That is not the problem. It doesn't matter what algorithm you write, and it doesn't matter like what computer you make. You can make a quantum computer if you want. To solve this problem, it will take more time than say 1,000 billion years. Okay? So this tells you that this problem is fundamentally hard. It is not about algorithms at all. The problem itself is fundamentally hard. Okay? And that brings us to the third thing, which is complexity theory, which is essentially what I do, and which started somewhere around like 1971, basically by 2-3 papers, okay, by papers of like Cook, Levin, and Karp. Okay, that how fast can you find a proof? That tries. So basically, what does complexity theory do? It tries to understand sort of how inherently difficult problems are. Doesn't matter what algorithm you are going to write for that problem. I give you some problem, okay? Something you pick up on lead code, okay? I give you some problem, then you write an algorithm for it. So this is not about algorithms at all. It's about, in some sense, it's not about any specific algorithm. And in some sense, it's about every algorithm. Because what I'm saying is, what is it that any algorithm, so it's like understanding every algorithm for a particular problem, okay? So complexity theory basically tries to understand this thing, like how inherently difficult problems are. Okay? Yeah, and independent of any algorithm. And all of these things are like at the core of mathematics and philosophy, basically. Like you take logic and philosophy and mathematics and basically complexity theory and computer science, all this is there. Okay? So I think this is all I thought I'll say. And yeah, I think you guys can ask if you have any other questions.
I mean, if anybody have any queries, then they can raise their hand. But it was very fundamental session. I mean that this fundamentals, I mean, I have not thought any time that there is so much importance which can be given to this thing also, which we assume is it to be true always.
Yeah. It's like whatever you assume becomes your axioms. Okay? So you can't assume everything, right? Like you can even start with an axiom which says 1 + 1 = 2, but then you'll not be able to prove anything because it's too like your axiom should be extremely basic. So if you take basic enough axioms like the Zermelo-Fraenkel axioms, it's like called ZFC, then yeah, you'll have to prove that 1 + 1 is 2, basically. So
yes, basically what we and whatever, I mean, most of the people who are attending here are up to is that we have been taught about all the algorithms, we see about, we solve the problems, we do competitive coding. But I think that this is very fundamental thing, that it's a new thought which we can actually provoke, and we can think in this perspective as well.
Yeah.
To solve the problem statements as a whole.
Yeah.
And if many of you might be having any questions, right, to be asked, then they can come forward and ask. Some of the questions I have also received, I will ask them. But before that, if anybody wants to come forward and just, you can interact. I mean, it's an interactive session, so come forward and do ask upon. Let me start at first. That one or two people, I mean, some have asked that you have done PhD, right, after your BTech. So after BTech, you have done PhD. So how difficult it is to directly get admission into PhD? Generally, it's taken from PhD, then we do MTech, and then we go to PhD. So and how difficult it is to, is it? I think that yeah, Jenish is my brother, and I know that he has got a job offer from Yahoo at that time. So how the decision was made not to take offer and to go to PhD? So
yeah, I think it's just about you, basically. Personally, how you are. Like my temperament is extremely academic. Okay, like everything I do is like, I think in a very, very academic way. So then that's like it's like the most like natural thing personally for me. So I went for the PhD, and I think in like it's like different fields of things in different way. Like most places you do PhD after BTech. In some other places, like if you're not sure whether you want to do a PhD or not, then people do a master's, basically, to just like try and do some research and see if they enjoy it, and then go for a PhD or something like that. And then some programs only have like direct PhD things. You don't have any masters at all, basically. So yeah, I mean, it depends on how you are, basically. And just based on how you are, you can like,
Yes.
it's up to you. It's a very personal thing. Like if you are academic, then it's like the most natural thing. So
okay, but I mean that we need to write research papers as well, right, to get admission into good colleges. So which are the fields or research domains which one should focus in the current emerging era? I mean, is there anything you would actually like to guide that, okay, you can focus on this lot right now and study them?
like I'm not an astrologer, so I don't know how things happen. Like I mean, yeah. So I mean, if I knew that, then I would be doing something different, right? So like I mean, I don't know. Like any things will change, things can happen, whatever. But I mean, it's like it depends on what you like. Ultimately, everything will boil down to like what you want, right? Like what do you really want? If you don't want anything, that is also fine, right? That's the like me. Like then you're like me. I don't want anything, basically, right? So like if you want say money, then you should just go into finance and do something there. Okay. If you like, it depends on what you want, right? Like if you want like fame, then you can be a YouTuber or whatever. If you want like, I mean, it depends on what you really want, right? Like if you want to make some social change, then you can create some like, I don't know, social organizations and stuff. Like it depends on what you really want to do, and based on that you will like select what you want to do. Sometimes people have like limitations, like if you have to support your family and everything, then you'll have to get some job somewhere, right? And then you'll have to have the skills which people generally these days, everyone is learning machine learning, basically. Like people don't know probability and then they do machine learning, which is very surprising to me, but still people do it. So like you should like, whatever is happening first, I think the basic thing is like you should do everything very like thoroughly, like not just to finish things like, okay, this is some data set, I need to like fit some algorithm and then submit. It's much more important to like very fundamentally understand what you are doing. Okay. Because then you'll really progress very, very far. Like if you don't, then you'll always stay at like just of some points. Okay. So if you want to progress far, it's not even necessarily to progress far.
Yes,
You
actually,
can
it's very difficult for us to stay with one problem for a longer span of time, which most of the people which I have met face a difficulty in. Staying with one problem is more difficult than switching to new problem, and so maybe that's the hindrance which is.
Yeah, I think another thing is maybe you can work in a group. Then sometimes problems people enjoy doing them. Like if for example, when I do my research myself, I like doing myself only, so I do myself. But then say if you are solving some data set and you have to focus a lot, and if you think you are getting stuck, then you can have your own study group or something. You can have like, you get it right, like you can gather some 4 or 5 people and do it together. Then it might become like much more like interesting, basically, than like doing it by yourself, maybe.
Yes.
But I
So for
think
that,
yeah.
for that only, I think that we are promoting this community culture as a whole over here. That if we have community and if we have different domains where a group of people can work together.
Yeah, that is good, that is nice. Yeah,
So we are promoting that culture so that
yeah.
if we are stuck, then we can get to do that together.
Yeah.
If anybody else have any queries, then they can also come forward, and we will be organizing more events. We are a part of Clique Community, and right now we have collaborated with Ahmedabad University IEEE branch and MBIT IEEE branch. And right now we are doing such a program named Internship 3.0, where we actually collaborate and we create group of people who work in a particular domain of their interest. So if they are stuck anywhere, if they don't know, and if they are just going to migrate from that domain, then they can actually have a team who can actually work together and they can work more upon the project ideas. So
I can actually say one thing maybe which might be helpful to everyone, because like I see so like you were even asking me some random questions yesterday. So I think I think I think people have many like misconceptions, and everyone has them, and they have them forever, and they live and die with their misconceptions. That like people tell you that, oh, it's very important to have passion, oh, it's very important to have positive attitude, oh, you need determination. All these things are like whatever. None of these things. I think these things just people say, but like some negative attitude sometimes is way more powerful than positive attitude. Sometimes this is how reality works. Okay, it's like so so there are like so many factors and a billion things that come together. So there is no clear sequence of steps that you have to do and you have to take care of so that everything will happen fine and stuff like that. Okay, but there is like one very fundamental quality which I think like people should just cultivate if they don't have it. But if you have it, it's good. And I think that is like the ability to bear pain. Okay, if you can't bear pain, like that is the most fundamental thing. Like you should be able to go through pain. Okay, because when you learn something new, it will be extremely painful. Okay? But like that pain is so fundamental and so crucial, that is like the very like sort of universal quality that takes people very, very far. Okay? So I think that's why there's this one quote. All quotes are always rubbish and they are very contextual and they can apply only in a certain situation, right? But this one is actually it's very nice, and it says something like it's by Khalil Gibran, and it says that like your pain is the breaking of the shell that encloses your understanding. Okay? So it's exactly like that. So everything you do, if you can't go through pain, there is no point in doing anything. So yeah.
Yes, it's very truly said.
I mean, it's. I mean, you'll just observe it as you live more life. That
I have one question.
Yeah,
So
yeah.
can you suggest me some books on a probability and statistics? Like, I'll say I started learning about it, but I could not find anyone.
Yeah, so I think Feller's Probability is like a very standard book. It's by Feller, Feller.
Okay.
So he has written. So I think okay. So this is one thing. One of the best ways to learn anything today is books are very good. They are really awesome because that's like a story. But a nice way is to go through lecture notes of different courses. Like everyone has their lecture notes online. Like you can take like all probability courses of all universities in the world, and they'll have everything online, right? And if you like, for example, like I am like sort of TAing one course for one of my advisors, like Leonard Schulman. He teaches like probability and algorithms. So he has a course, but it's like a super advanced course. He has a basic course also, but his basic course also is like, I think, sufficiently advanced. But you'll always find lecture notes, which I think is the best way to learn. And another thing I realized is that you ultimately like no book can teach you anything, like really, like no external agency or person or object or book can teach you something. Okay? Ultimately, you have to arrive at something by going through that pain. Okay, you have to keep that idea in your mind for sufficiently long, and then at one point you'll understand it. Like if you don't understand like say permutations or combinations, you'll have to just like keep thinking about it, keep trying, like keep thinking of random examples yourself. That if I have this much and if I pick this much, what will happen? If I have this and if I do that, what will happen? Just ask, don't look at any books or anything, just try to like think through yourself. And that is like the best way to understand, because then you'll never forget it. If like yeah, so I think once you like the axiom of choice, like I arrived at it before I even knew that there is an axiom of choice. Like I felt that an axiom of like this should be required, and then when I learned about it, I felt very good. Okay, there is something like this already, right? So it's like when you come to some concept yourself, and it happens to everyone, it's just that you don't stay with the concept long enough. If you give up on it, then you'll never reach it. Okay? If you just stay for it with sufficient time, it's like sort of like it's like melting a rock with water. Okay, you have to keep pouring and pouring and pouring, and you'll keep chipping a little bit at a time, and then eventually it will break, basically, right? So something like that. So you can use, I think there is Feller's Probability, and I think better than me, I think the best way to learn would be just like go to these lecture notes, like wherever anyone has lecture notes, and they'll have resources in the course. So they'll have suggested textbooks, and you will find like take any standard university, like take like Caltech or like whatever, MIT or Stanford or Princeton or something, Berkeley, whatever. Take any university, take their courses, look at what books they use, and just read those books, basically. So
okay,
and you can always find copies of those books online, right? You can always find some PDF online, so you don't need to like buy it, basically. You can take a pirated book. It's completely good. Yeah. So
Okay, fine. But I'll just check the Feller's book first.
Yeah. I think it's a very standard book, Feller's Probability. There are 3 volumes, so you can just even if you start with the first volume. So yeah, I mean there are many beautiful probability books. Like Lovash has a book which is so good. I mean there are many books, but maybe the standard one is probably Feller. So
okay, fine. I'll just go with it.
yeah.
Thanks.
Yes, come on, any participant who has any query, then we can just address that and then we can wrap up the session. If anybody have, then don't hesitate to come forward. Okay. Yes, Jenish, it was a very motivating session. And I would really like to thank you to come here, to give time over here and actually motivate us. I mean, I think that we really need some motivation and also the perspective of thinking about the importance of mathematics in the domain of computer science. Because I think that now we are just so much in this, especially after this time of COVID and everything, we are just thinking to get a job, most of us, and then just practicing the codes and everything. But sometimes to know the fundamentals is also a very vital thing to know.
I mean, it depends. Like if you enjoy it, then it is vital. Like
yeah.
If it makes you happy, then it is very vital. Because it's like once your mind goes to another level of thought, it'll never come back to that previous level of thinking. So once your mind like progresses, you will see the whole universe in a completely different way. But for that, you'll have to keep going through the pain all the time of learning new things, basically. So
yes. So I hope that all of us takes more amount of pain and go through.
it's not that you have to take pain, but whenever it comes, you should be able to like understand.
You should be able to, yeah, exactly. I think that nobody else have any queries especially to be addressed, right? And Jenish, thank you so much for giving your time to this session. It means a lot to most of us to actually hear from you about your experiences and all the fundamentals which you actually helped us to clear.
Yeah, it's completely fine. Yeah.
So
okay,
so have a very good Saturday, all of you, and enjoy your weekend, and do think about the things which we have discussed today. And yeah, we will definitely come forward with more events, upcoming events, and I hope you can follow us in the links which we have provided in the chat. So we all will, I mean, together do more events together. But this was really a phenomenal session as a whole. So yeah, goodbye to all of you. And
bye.
Thank you, Jenish. Yeah, it was a really good session.
Thank you.
Bye.
Bye.
Thank you. It was a really informative session.
Thank you. Thank you so much.
Jenny.